Welcome back, guys. After discussing the basics in the nerve physiology, now let's discuss a very important topic and highly conceptual topic. Okay, in the nerve physiology, we are going to discuss about a resting membrane potential. See, this resting membrane potential is not something only present in the neurons, but it is also present in most of your body cells. It's also present in all of your body cells. Okay, but in order to understand action potential, before that you need to understand the resting membrane potential. Okay, so now in this video I'll be discussing about the resting membrane potential in detail. Okay, so this is a highly conceptual topic. A lot of calculations are going to come, highly conceptual. So I want you to be absolutely attentive. Okay, having said that, without any further late, now let's discuss about resting membrane potential. In the short form, you can call it as RMP. Okay. Now in the beginning itself, I am telling you, resting membrane potential and action potential, they are not same. So resting membrane potential of a cell and the action potential, okay, they are not same. They are totally different things. Okay. Resting membrane potential is present in all the cells. Okay, all cells of your body, almost all cells have the resting membrane potential. Action potentials are seen in those cells which are usually excited. Okay, for example, like neurons, okay, muscles. Okay, so in muscles there will be action potentials. Action potentials, it's a totally different topic. Now in this video, let's see what is the resting membrane potential. So in the name itself, it's a resting, during a resting condition, and a cell is not excited, it's not stimulated, it's absolutely resting, it's in equilibrium. Now when it is in equilibrium, there is a voltage difference, okay, outside the cell and inside the cell. There is a voltage difference inside the cell when compared to the outside the cell. Okay, first of all, let me show you here. This is one cell. Okay, here is one cell. When compared to the outside, okay, when compared to the outside, your cells are having a voltage difference inside the cell. For example, if I ask you what is the resting membrane potential of a neuron, you will immediately say the resting membrane potential of a neuron is minus 70. Okay, minus 70 when compared to outside. Okay, minus 70 millivolts. There is a voltage difference across the cell membrane when compared to outside. Inside the cells, there is a voltage difference, minus 70 millivolts. Okay, if I ask you what is the resting membrane potential of a cardiac myocyte, you say minus 90 millivolts. Means when compared to the outside, inside the cell, there is a voltage difference. How can you measure it? You can measure it by keeping an electrode here. You can just keep an electrode outside the cell membrane, and you can connect an electrode inside the cell membrane. You can keep electrode inside the cell membrane, and you can just connect these two to the voltmeter, and the voltmeter is going to show the what is the voltage difference. Okay, so let's write in the form of a definition. What is resting membrane potential? The resting membrane potential is the difference in the resting membrane potential is the difference in electrical potential across the plasma membrane. When the cell is not stimulated. Okay, or in an easy way you can say that is resting membrane potential, that is it's a voltage difference between inside of the cell when compared to outside of the cell. Okay. So what is the usual range of resting membrane potential? Our cells are having resting membrane potential. Now what is the normal range? The range will be somewhere between, range can be somewhere between minus 10 millivolts to minus 90 millivolts. Okay, this is the normal range of resting membrane potential in the different types of cells. Now, first of all, what is creating this resting membrane potential? Why there is this difference across the cell membrane? Why there is this difference? Okay, why there is this voltage difference? Outside there is positive and inside there is a negative. Okay, almost all the cells are having negative resting membrane potential. So what creates, let me write here, what creates resting membrane potential? Okay, there are different things. First thing is the concentration, the difference, or you can say uneven distribution of ions. There is a concentration difference or uneven distribution of ions across the cell membrane. So what I am trying to say is, see the amount of ions, the number of ions in the extracellular fluid and the number of ions in the intracellular fluid. Okay, see for example here is the cell membrane. Now the amount of ions in the extracellular fluid and the amount of ions in the intracellular fluid is not same. The ions are unevenly distributed. Ions are charges. Charges are responsible for the voltage. Okay, so there is uneven distribution of ions across the cell membrane, and that's one of the factor for the generation of resting membrane potential. Okay, now you can ask me why there is this concentration difference. Okay, why there is this concentration difference? Why the ions are unevenly distributed? So that is explained by a phenomena, okay, or effect that is called as Donan's effect. So this uneven distribution, okay, this uneven distribution, and these ions are unevenly distributed, and it's always like that. Okay, they are not getting equal. Okay, so this uneven distribution is due to something called as Donan effect. Okay, so this is the reason number one. And during resting state, normally during resting state, your cell membrane is selectively permeable. Okay, so it is showing some bias. Why it's showing some bias? Normally, see the cell membrane, what happens is the cell membrane during resting condition, even during resting condition, it allows certain ions to pass through the membrane, and it doesn't allow certain ions to pass through the membrane. Okay, some ions are having the pass, they are having the pass to cross the cell membrane, and certain ions are not allowed to cross. So there is this bias. So because of this, certain ions are going to be present within the cell and the certain ions are going to be present outside the cell. So there is unequal distribution. So this is also due to selective permeability. Selective permeability of cell membrane. So that's why we say your cell membrane is semi-permeable. Okay, semi-permeable means it allows certain ions to pass through and it doesn't allow certain ions to pass through it. So what creates the resting membrane potential? The resting membrane potential is due to unequal distribution of ions across the cell membrane, in and outer leaflets. Okay, when compared to the inside of the cell, there is a difference in the concentration of ions out of the cell membrane. Okay, and why it is like that? It is due to an effect called as the Donan effect. We are going to discuss about this Donan effect in detail. Don't worry about that. Okay, this is one thing. And one more thing is this unequal distribution. Okay, this unequal distribution is also due to leaky channels. Okay, especially potassium efflux via leaky channels. It also accounts for the development of the resting membrane potential. So during resting condition, Okay, during resting condition, the major ion, which is the potassium, it always goes out of the cell. It always crosses the cell membrane and going out of the cell membrane. Okay, potassium is having pass. It is permeable. So potassium is going out of the cell membrane. Potassium is a positive charge. Positive charges are going out of the cell membrane. Okay, so that will also contribute to resting membrane potential. How, we'll discuss later. Okay, this is one of the reason. Next one is, there are certain pumps called as sodium potassium pumps or ATPases. The sodium potassium ATPases, what is the coupling ratio? The coupling ratio is 3:2, which means it sends 3 sodium out of the cell and bring only 2 potassium into the cell. So 3 sodium are going out, and only 2 potassium is coming in, which means more positive charges are going out of the cell, and less positivity is coming into the cell. So less positivity is coming in, more positivity is going out. So that will also contribute for the development of resting membrane potential. Okay, I will explain in detail how the resting membrane potential is created. But the point number 1 which I want you to know is, there is unequal distribution of ions. Okay, the unequal distribution of ions are there. That unequal distribution of ions is due to Donan's effect. Your cell membrane is selectively permeable. Okay, selectively permeable. It allows certain ions to pass through the cell membrane easily. So potassium, it crosses the cell membrane always from inside to outside. Potassium is leaking out always via the leaky channels, not the voltage gated channels, just the leaky channels are there. They're always allowing the substances from high concentration to low concentration. So there are potassium leaky channels present on the cell membrane. So potassium is going out, positivity is going out, positivity is going out, positivity is going out. So cell will become negative. There are pumps called as sodium potassium ATPases. These sodium potassium ATPases throws more positivity out of the cell and brings less positivity into the cell. That will also contribute to negative resting membrane potential development. Okay, almost see this ATPase, it requires ATP for its function. Okay, almost 25% of the energy in your body, 25% of the cellular energy will be used for this sodium potassium ATPases. But MCQ purpose, the point which I want you to know is, see, the resting membrane potential, okay, is due to leakage of potassium. True, leakage of potassium creates the resting membrane potential. Sodium potassium pumps creates the resting membrane potential, but it only contributes to 5 to 10%. Okay, it only contributes to 5 to 10% in the development of the resting membrane potential. Oh, okay, very less. It's a potassium efflux. Okay, it's a potassium efflux which is a major determinant. Okay, positive charges are going out, so inside becomes negative. So let's go one by one, step by step. First, let's discuss about what is this Donan's effect. Okay, Donan's effect. So let's write here. Donan effect. See, I want you to know, when the life originated, okay, when the life is originated, okay, in the beginning itself, when the life is originated, see, for example, here is a unicellular organism. For example, this is one cell. Where the life is originated? Life originated in the sea. Okay, life is originated in the sea. So in the sea, which ions are more? Can you tell me which ions are more? There are more sodium chloride. Okay, sea means salt. There is more sodium chloride. Okay, so even till to this day, in our body, to maintain the cellular physiology, to maintain the homeostasis, even our cells, they keep the same concentration. Okay, they keep the same environment around them. So our extracellular fluids are having more amount of sodium and more amount of chlorine, even in our body right now today. Of course, the concentration may be little different. The concentration wise, the fluids are more diluted. Okay, but the point is, even to this day, the extracellular fluids are having more amount of sodium chloride, and our cells are having more amount of potassium in. Okay, so cells intracellularly, which ions are more? Potassium is more inside the cell, sodium and chloride are more outside the cell. Okay, So can I say something like this? Cells are life originated in seawater. So extracellular fluid have similar composition to seawater. That is, the extracellular fluids are rich in ECF is rich in sodium and chloride. Okay. Now, after this, let's explain you what is this Donan's effect. Okay, what is this Donan's effect? To have a better understanding about this Donan's effect, I told you Donan's effect, what it is creating, it creates this Donan's effect is the one which creates unequal distribution of ions across the cell membrane. Okay. Why is such? Let's look here. This is okay. Here I am showing you two compartments, compartment number A, compartment number B. Here I am showing you two compartments. Okay. Now these two compartments, they are separated. Okay. For example, let's separate these two compartments. Compartment A and compartment B are separated. Where this red line here is the semi-permeable membrane. Okay, this is the semi-permeable membrane. Okay. Now let's take this this membrane. Okay, it's allowing the substances to pass through it. Now here in the compartment number A, what I am keeping here? Sodium. I am adding sodium molecules. How many sodium molecules I am adding? 9 sodium molecules I am keeping here. And in the compartment number B, again here also I am adding sodium. Of course, water is there. Okay, let's say here total water is there. Okay, I am not showing it, but understand. In compartment number A, how many molecules I kept? 9 molecules of sodium. In compartment number B, how many molecules of sodium I kept? 9 molecules. Sodium is a positive charge. So 9 positive charges here, 9 positive charges here I kept. Okay. So now you tell me, sodium is going to move from compartment number A to compartment number B or from B to A. In which direction sodium is going to move? See, the concentration of sodium is 9 here, here also 9. So as the concentration is same, there is no net movement. The sodium is not going to move. Okay. Now here in the compartment number B, I am keeping the chloride. How many chloride I am keeping here? 9 chloride I am keeping here. So what happens if I keep 9 chloride molecules? Okay, the negative charges. What happens? Here there is no chloride. So automatically this chloride will try to undergo diffusion. Okay, it want to undergo diffusion and create an equilibrium state. Balance. Okay, there should be always balance. Okay, substances should not be concentrated in one single place. Okay, so now here look what happens is there is no change with the sodium. Here sodium is 9. Here also sodium 9 ions are there. Now what happened to the chloride is here chloride 4 ions. Here chloride 4 ions. Okay, so here 9, right? Total 9, right? So equally distributed, 4 and 4, 8. But 1 ion is left over. So what is this 1 ion doing is this 1 ion, chloride ion, is shifting from this compartment to this compartment and this compartment to this compartment. It is like shifting. Okay, equilibrating, balancing here and there, it's balancing. Okay. So this is what is normal. So in a normal model cell, perfect ideal model, the ions are getting balanced, equilibrated. Now what I am doing is I am going to explain you the Donan's effect. Now into this compartment number A, I am adding a large impermeable molecule. So here I am adding, look here, proteins. Now proteins are which charges? You know, proteins are negative charges. How many proteins I have added? 9 molecules. 9 negative charges I have added. So now what happens? See, Donan's effect says in the presence of an impermeable molecule, in the presence of impermeable molecules like proteins. First I will write the definition so that later we can understand. Okay, in the presence of large impermeable molecules like proteins, the distribution of permeable ions will become uneven. Okay, so what I am trying to put in your mind is, in the initially say these are the permeable ions, sodium chloride, they are permeable. Okay, so they are equally getting distributed, here 9, here 9. Okay, here 4, here 4. So they are getting equally distributed when the proteins are not present. But when you add proteins, now I am adding the proteins, these proteins are impermeable. Okay, these proteins are impermeable. Now, under the effect of these impermeable molecules, now the distribution of the permeable molecules will become uneven. Now they will be unequally distributed. From the beginning I am telling you this. Across the cell membrane, due to Dominant's effect, the distribution of ions will be uneven. The concentration of ions outside the cell and the concentration of ions inside the cell is not even, it is uneven. That is due to Dominant's effect. Okay, I will explain you. Now look, what is happening? Now you have added the proteins. As you have added the proteins, what happens now? Look at the equilibrium. What happened to the equilibrium? Equilibrium is same. Now what happened? You have added, see here, now I am adding proteins. If you add proteins, how many molecules of proteins you have added? 9 molecules of proteins you have added. Okay, here. Now tell me, here you are having more negativity. Okay, more negativity. Now what this negativity will do? Two things it will do. It will, according to physics, like charges repel. This negativity is going to repel the negative ions. Okay, so chloride, now here 4 chloride ions are there. But when you add more negative molecules like proteins, now the protein is not getting equilibrated, it's not permeable. So protein is sitting in the compartment number A. So this negative charges, what they will do is, they will kick the chloride into compartment number B. Like charges repel the like charges. So chloride will shift into B. The same negativity is going to attract the positive ions. So this sodium ions are going to be attracted and the chloride ions will be repelled. Okay, again to maintain the equilibrium. You have to maintain the equilibrium at the end of the day. So what happens is, look here. Now here is compartment number A and B. Now in compartment number A, what happened to the number of sodium ions? Sodium ions were initially 9 in number. Now it becomes 12 here. Now what happened to the sodium here? It becomes 6. Initially number of chloride ions here, how many? 4 are there. One is moving here and there. Now chloride ions are becoming 3. Here the chloride ions are becoming 6. Okay. Here what else are there? Proteins are there. How many protein molecules? 9 protein molecules. Now equilibrium is attained. Equilibrium is attained. You might think, sir, how equilibrium is attained? Okay, how equilibrium is attained? What kind of equilibrium is attained? I will tell you. See, here compartment number A is happy and compartment number B is also happy. You might think, why they are happy, sir? See, the number of positive charges in compartment number B is 6 and the number of negative charges in the compartment number B is 6. So 6 positive charges are there and 6 negative charges are there. Positive, the number of positive charges and the number of negative charges is 0. So this compartment number B is electroneutral. Okay, electrically it's neutral. Okay, 0. Okay. Now look here. In the compartment number A, how many positive charges are there? 12 positive charges are there. Okay, 12 positive charges are there. Now, how many negative charges are there? Chloride is negative charge, 3 plus 9, 9, 10, 11, 12. So, totally 12 negative charges. Okay, sorry, mistake here is 9, right? 9 minus. So, total 12 negative charges are there and 12 positive charges are there. The number of positive charges and the number of negative charges are equal. So, even the compartment number A is electron neutral. So, equilibrium attained. So, electrically equilibrium is attained. So, here electrically it is neutral, the compartment number A, and the compartment number is electrically neutral. Okay. But look at the number of ions. See here in the compartment number B, how many ions are there? 6 plus 6, 12 ions are there. And how many ions are there within the compartment number A? So, 12, okay, plus 3, 15, okay. 15 plus 9, 24, means more ions are there. So, in one compartment more ions are there, in the other compartment less number of ions are there. So, across this membrane, now ions are getting unequally distributed. So, due to the presence of these molecules like proteins, of course in our cells proteins are there, okay. Due to the presence of proteins, the ions are getting unequally distributed. If proteins are not there, they are equally distributed. But due to the presence of this large molecules like proteins, impermeable molecules like proteins, the ions are getting unequally distributed. Even though they are unequally distributed, both the chambers are maintained electron neutrality, 0, 0, no, there is no difference. So, what is the voltage difference between these two? Voltage difference is 0 because here it is 0, here it is 0, okay, but voltage difference is 0. Now, what I am trying to put into your mind, resting membrane potential is attained? No, resting membrane potential is not attained. Resting membrane potential, we say the voltage difference minus 90 millivolts, minus 70 millivolts. So far what I have discussed with you, the Donan's effect. What this Donan's effect is doing, the first step, Donan's effect is creating unequal distribution of ions. So, in the compartment number A, more number of ions are there, and in compartment number B, less number of ions are there. But both the compartments are electroneutral. Okay? And due to this Donan's effect, as both the compartments are electroneutral, any resting membrane potential is generated, any voltage difference is generated? No. Resting membrane potential is not generated, no voltage is generated because both chambers are electroneutral. Okay? So, what we have to know? We have to give an equation. We have to write certain important points. So, that is Donan's equation or Gibbs. So far whatever we have discussed, same things are explained by Gibbs-Donan equation. Okay, Gibbs-Donan equation. So first point number 1, the total number of, look at the compartment number A, total number of positive charges in compartment number A. Okay, the total number of positive charges in compartment number A is equal to total number of positive charges. The total number of positive charges in compartment number A is equal to total number of negative charges in compartment number A. So, in compartment number A, again look, the number of positive charges 12 and the number of negative charges is also 12. Okay, and same thing, okay, I shouldn't write a second, the same thing, total number of positive charges in compartment number B should be equal to total number of negative charges in compartment number B. So, here look, in compartment number B, the number of positive charges are 6 and the number of negative charges are also 6. So, 6 and 6. So both the compartments are electroneutral. Okay, both the compartments are electroneutral, electrically neutral, no difference. Now, what else are given by the Gibbs-Donan equation? The product of ions in the compartment number A, the product of ions in compartment number A. For example, look, what is the product of ions? The product of ions is, how many ions are there? See, for example, 12. I am talking about only the permeable ions. I am only talking about the permeable ions. Okay, I am not talking about the proteins. Product 12 into 3. 12 3s are how much? 36. So product of permeable ions, let's give the P here. Product of permeable ions in compartment number is how much? 12 into 3, that is 36. That should be equal to the product of permeable ions in the compartment number B. Product of permeable ions in compartment number B. How much is that? 6 into 6, that is also 36. Look here, 6 into 6, same. Okay, products are same. Now what else? I told you in compartment number A, more number of ions are there. Wherever the more number of ions are there, osmolarity will be more. Okay, so there is difference in the number of ions. There is difference in the number of ions. In compartment number A, more number of ions are there. Wherever the more number of ions are there, ions are responsible for the generation of osmolarity. Okay, so wherever there is more osmolarity, there will be fluid shift. So there will be fluid shift from compartment number B to compartment number A. So let's write here. Third thing which I want you to know, osmolarity in our example compartment number A is greater than compartment number B, which means there are more ions in compartment number A, and in compartment number B there are less ions. So here itself we can understand there is unequal distribution of ions. In compartment number A, more ions are there, and in compartment number B, less ions are there. Okay, so let me show you the same thing. Okay, here with this the Gibbs-Donan equation is completed. So Gibbs-Donan equation is telling you about the compartment number A and the properties of compartment number A and the properties of compartment number B. Finally, you should know both the compartments are electron neutral. There is no development of resting membrane potential so far. Okay, now let me show you the same thing here. This is a cell. Okay, now tell me, here in this cell, imagine this is one compartment. Okay, compartment number A. Okay, our cell, this is the compartment number A. Okay, here is the compartment number B, outside compartment number A and compartment number B. Now here more ions are there or less ions are there? Inside the cell. Inside the cell there are more number of ions present. See, now I am showing you here. For example, 1, 2, 3, 4, 5, 6, 7, 8. For example, let's say 9. 9 positive charges are there. Both the compartments are electroneutral, which means the number of positive ions and the number of negative ions should be equal. Okay, should be equal. If there are 9 positive charges in the compartment number A, how many negative charges should be there in the compartment number A? There should be equal number of negative charges. So equal amount of negative charges are present here. Equal amount of negative charges. Okay, and in the compartment number B, look here. Here also positive charges are there, and here also negative charges are there. Now look, in the compartment number B, the number of positive charges, for example, 1, 2, 3, 4. And how many respective negative charges should be there? 1, 2, 3, 4. But I have told you, in one compartment, there are more number of ions. In the other compartment, there are less number of ions. But the number of positive charges and the number of negative charges are equal. So here this is electro neutral, means 0. For example, neutral. Okay, there is no positivity or no negativity. Here also inside this compartment, the number of positive charges, of course the number of ions are more, but the number of positive charges and the number of negative charges are equal. So this compartment is also electro neutral. So here also 0. So any difference is there in the voltage between inside and outside the cell? So far, no. So there is no difference in voltage. So far, up till now. So next, how the resting membrane potential is generated? What is the next step in the development of the resting membrane potential? So now, let's, after discussing about the Doran's effect, how the unequal distribution of ions is created, now let's see how our human cells are. Okay, now I am talking about the human cells. In our human cells, the first point which I want you to know is, imagine this is our human cell. Now, human cells, they have these leaky channels on them. Okay, there are certain channels called as the leaky channels, even during resting condition. Okay, see, these are the different leaky channels I am drawing here. Okay, there are different leaky channels. What they are doing? They are allowing, okay, they are allowing the leakage of ions even during resting condition, just resting condition mein, according to concentration gradient, according to the concentration gradient, they will allow the ions to pass out, okay, and pass in. So there is a potassium leaky channel, this is a leaky channel. Okay, leaky channel. And here, for example, this is sodium leaky channel. Here there is chloride leaky channel. So these are the leaky channels. Okay, these are the leaky channels. They are allowing the substances according to concentration gradient. Now, my dear students, what I want you to know is, here the chambers are electrically neutral. Here the chambers are electrically neutral. Means there is no electrical gradient, because outside 0, inside 0. There is no electrical gradient. But what I want you to know is, there is a concentration difference. Okay, there is a concentration difference in the amount of ions. Outside there are less number of ions, inside there are more number of ions. So there is a concentration difference present. Electrically they are neutral, but there is concentration difference. Because of this concentration difference, the ions will leak either in or out. So let me take you one typical human cell. Okay, imagine there is this one typical human cell. Okay, for better understanding, let's say here this cell is only having one type of leaky channel. It's having one type of leaky channel. And what is that one type of leaky channel? It is potassium leaky channel, which is most common, and most of our human cells are having maximum number of these potassium leaky channels. Okay, now look here, our human cells, you know, they are having high amounts of potassium. Intracellular potassium is more in the human cell. There are lots and lots of potassium in all the human cells. Lots and lots of potassium is there. Okay, for example, 1, 2, 3, 4, 5, 6. 6 potassium molecules are there, just for understanding. Okay, if 6 positive charges are there, means how many negative charges will be there inside the cell? 6 negative charges will be there. Okay, negative charges are also there, maybe phosphate or chloride. Negative charges are proteins, negative charges are there. Means the number of positive charges and the number of negative charges should be equal. But the point is, see, potassium is more inside the cell and the potassium is less outside the cell. You know it, potassium concentration outside the cell is less. So I can clearly say there is a concentration gradient for the potassium. Okay, there is a concentration gradient for the potassium. Potassium is more inside the cell and less out of the cell. So potassium will try to go out of the cell. Potassium will try to go out of the cell. So this potassium, what it is doing? It is going out of the cell. Why it is going out? Because your cell membrane is selectively permeable. Your cell membrane is having this leaky potassium channel. Due to the presence of this leaky potassium channel, potassium is going out. Okay, potassium is going out. So one positive charge is going out. So your positive charge is going out. Your cell membrane is only permeable to potassium, not to this negative charges. So one positive charge is going out. Along with that one positive charge, even negative charge is going out, because they are like together. Okay, they are like boyfriend and girlfriend. Okay, now this positive charge potassium is going out. Along with the positive charge, even negative charge will try to go out. Okay, but your cell membrane is only permeable to here, potassium, not to this negative charge. So negative charge is unable to go. Okay, so you are losing the positive charges. So what is remaining inside the cell? Negative charge is remaining. So potassium is going out constantly. Potassium is going out constantly. So as the potassium is going out, who is left over inside the cell? Negative charges are getting accumulated. Negative charges are getting accumulated. So now you understood. So who is developing? Voltage difference. The positive charges is going out. So outside the cell, what is developing? The positive charges are going out. Potassium is going out. So outside the membrane, there is positivity. And inside the cell, what is getting developed? Negative. So for the first time, we are saying there is a difference in the voltage. Outside is becoming positive, inside is becoming negative. So for how much time this potassium will go? For how much time it will go? See, potassium is going, potassium is going, potassium is going. But there will be a time, see, what is happening inside the cell? Negativity. Negativity. Okay? Now, what will happen is, sir, negative charges are going to attract the positive charges. Okay, negative charges are going to attract the positive charges. So there will be a time that this negativity, whatever the negativity that is developed, this negativity, see, positivity is trying to go out, but there will be a time that this negativity will not allow this positive charge to go out, the potassium to go out. Means again equilibrium is happening. So for certain time the potassium will go out. Because of the movement of potassium inside the cell membrane, negative potential is getting developed. At certain time, this negativity will not allow the potassium to go out. So potassium movement stops because of the development of this negativity. That negativity is not letting the potassium to go out. Okay, so that voltage, see, that voltage where the net movement of potassium out of the cell, net movement of potassium out of the cell, now the potassium is not able to go out. So that voltage is called as, or that potential is called as equilibrium potential or isoelectric potential. So let me write here. First, what happened? According to the concentration gradient, potassium try to go out. Okay, first let me write here. So concentration gradient allows the movement of potassium out of the cell. Okay, we have seen potassium is going out because of the movement of the potassium. Outside membrane become positive, inside membrane is becoming negative. Next, what happened finally? Electrical gradient. Okay, now electrical gradient, look at the electrical gradient. Now this negativity is opposing the movement of potassium out of the cell. Okay, so electrical gradient is opposing after some time, okay, the electrical gradient is opposing movement of potassium out of the cell. So finally what happened? Potassium movement stops. And what happened finally? So outside the cell become positive, inside the cell become negative. Potassium movement stops and the cell is in equilibrium. So at equilibrium condition, now what happens? At equilibrium condition, net movement of potassium through the cell membrane. How much? 0. Okay, net movement of potassium is 0. Now look at the cell. I have shown you the same cell. See here. Now this is the cell. Now you know inside the cell what is there? Potassium is there. Okay, that potassium is going out through this leaky channel. Through this leaky channel, what is happening? The potassium is going out. Okay, and inside the cell, negative charges are also there. These negative charges are not going. Only who is going out? Potassium is going out. Because of this, outside membrane become positive, positive, and inside the cell it becomes negative, negative. Now, if you measure the electrical difference between this cell membrane, inside the cell membrane, outside the cell membrane, if you are measuring with a voltmeter, what you will see? There is a voltage difference. Okay. Which present during, okay, the voltage difference now it is present during the equilibrium condition. Now the cell is at equilibrium. Imagine now this cell is having only one type of leaky channel. This is a potassium leaky channel. So potassium is going out and the cell after some time equilibrated. After some time everything will be equilibrated. So there is no one like to move here and there. After some time there is net movement stopped. Okay. So now at the end there is a creation of the difference in the voltage. So voltage difference which present during equilibrium condition of the cell is called equilibrium potential or isoelectric potential. Okay, equilibrium potential or isoelectric potential, okay, of the cell or ion. Okay, equilibrium potential. Now what I want you to know is how to calculate the equilibrium potential. You know, you can simply measure it with the help of a voltmeter. What is the equilibrium potential? What is that voltage difference? You can measure it with the help of a voltmeter. But how to calculate it? Okay, so for calculation of this equilibrium potential, this is not resting membrane potential. Okay, this is not resting membrane potential. We haven't generated the resting membrane potential so far. Okay, I am talking only about one ion, one particular ion I am talking about. So potassium is going out. So that's creating a difference. So that difference is the equilibrium potential. It's almost equal to resting membrane potential, but you will understand little better. Okay, after some time you will understand better. So what is the formula to calculate equilibrium potential or isoelectric potential? Equilibrium potential of that particular ion. Okay, so the formula is Nernst equation. Okay, some will call it a Nernst equation or Nernst equation. Nernst equation. So the formula is equilibrium potential is equal to constants RT ZF log concentration of X ion, okay, so concentration of an ion outside the cell by concentration of the same ion inside the cell membrane, inside the cell membrane or outside the cell membrane. Okay, so this is the next equation. Equilibrium potential is equal to RT ZF. Those are the constant things. RT ZF log concentration of ion out of the cell and concentration of the same ion inside the cell. Okay, now what we can do is we can understand it better. So listen carefully. Equilibrium potential, now I am changing it. This is a natural logarithm. I am converting into log base 10. So I am multiplying it with 2.3 into RTZF log base 10, same concentration of ion out of the cell by concentration of same ion inside the cell. Okay, see here this RT by F value. Okay, so R gas constant, temperature, and F. See this RT by F value at room temperature. Okay, that's a constant value. its value is 26.7 millivolts. Okay, so now what I am going to do is I am going to put that in our equation. So equilibrium potential is equal to, okay, 2.3 into 26.7 by Z log base 10 concentration of ion outside the cell by concentration of ion inside the cell. Okay, this is all little mathematics, but don't worry, it's going to be easy. So final we have to derive one formula, okay, Nernst equation, so that it will be easy for you to understand how to calculate the equilibrium potential. Okay, now 2.3 into 26.7, I can say something like this: equilibrium potential is equal to 61 millivolts divided by Z, okay, log base 10 x out concentration of ion outside the cell by concentration of ion inside the cell. Okay, now this Z, what is this Z? This Z is valency of ion. So what is the valency for potassium? So K plus, potassium valency is 1. Okay, sodium valency is 1. For example, chloride valency is -1. Okay, something like that, valency. Calcium 2 plus 2, so that's the valency. Okay, so this is the final equation. So 61 millivolts divided by Z by valency log base 10 concentration of ion outside the cell divided by concentration of ion inside the cell. For example, okay, this is all mathematics, it's you might find it little difficult, okay, but at the end of the day, see, I have explained you, there will be an equilibrium, okay, there will be equilibrium, and during that equilibrium, okay, the potassium is going out, and that will create the equilibrium, and during the equilibrium condition there will be a difference, okay, there will be a difference in the voltage across the cell membrane, so that voltage, because of the leakage of this ion, is called as equilibrium potential of that particular ion, okay, equilibrium potential of that particular ion. Now for example, let's see, here I am showing you one cell, let's say here is one cell. So inside the cell potassium is there, outside the cell also potassium is there. Inside the cell the potassium concentration is 140 milliequivalents and outside the cell it is 14. So now what is it? Calculate the equilibrium potential of this potassium. Here the ion, the concentration of ion outside the cell and the concentration of ion inside the cell. Calculate the equilibrium potential. So how we are going to calculate it? With the help of Nernst equation. So the formula, you know it, 61 millivolts divided by Z. Here the valency, what is the valency? Potassium, potassium means K plus 1, valency is plus 1. Log base 10 divided by 14 concentration of ion outside the cell divided by concentration of ion inside the cell. Okay, so it will become 14 ones and 14 tens. So 61 millivolts by 1 log base 10 1 by 10. Okay, so 1 by 10 how much? So 61 millivolts by 1 log base 10, 1 by 10 means 0.1. Okay, so log 0.1 base 10, log 0.1 base 10, how much? What will be the value? So logarithmic table, if you check the logarithmic table, the value is going to be -1. So here 61 divided by 1, how much? It will be 61. 61 divided by 61 millivolts divided by 1, it will be 61 into -1. This whole value is going to be -1. Log base 10 0.1. Okay, it's -1. So how much? -61 millivolts. So the equilibrium potential of this particular ion in the cell, okay, the equilibrium potential of this potassium in this example, okay, normal equilibrium potential of the potassium is minus 90 millivolts. That's a total different thing. In this example, if you give the concentration something like this is like, you know, hypothetical concentration, like, you know, arbitrary numbers. These are just arbitrary numbers. So in this example, the equilibrium potential is -61 millivolts. Our isoelectric potential is -61 millivolts. Okay. Now, my question to you, this equilibrium potential, is it resting membrane potential? No, this is just equilibrium potential. This is not the resting membrane potential. For example, if only leaky potassium channels are there. Okay, imagine in this cell, only leaky potassium channels are there, no other channel, leaky sodium channel, leaky chloride channel, nothing is there. Only this one potassium channel is there. Then I will say, in this cell, the equilibrium potential is the resting membrane potential. Okay, but normally in our cells, only potassium channels are not present, only leaky potassium channels are not present. Of course, in certain cells, only leaky potassium channels are there. Of course, in the glial cells, only leaky potassium channels are there. But in majority of our cells, not only leaky potassium channel is there, but also other channels are there. Leaky sodium channel, leaky chloride channel are also there. So, when you take them into account, it's a leaky potassium channels, leaky sodium channels, leaky chloride channels, all of them, they will contribute, they will determine, and finally they contribute to resting membrane potential. Okay, one ion is causing equilibrium potential, but in our cells there are many leaky sodium channels are there, leaky potassium channels are there, and leaky chloride channels are there. Because of the presence of multiple different channels, you have to consider all of them, and all of them together determines the resting membrane potential. Okay, for example, let me write here the equilibrium potential of different ions. Okay, these are constant values, you should by heart. Equilibrium potential of different ions. You know, at equilibrium potential, the net movement of potassium is 0, net movement of sodium will become 0. When you are having this equilibrium potential, the net movement of ions is 0. Equilibrium is attained. Because of the movement of these ions, because of the movement of these ions, what happened? There is development of the voltage. Okay, so that voltage I am talking about now. So equilibrium potential of different ions. So sodium equilibrium potential is plus 63 millivolts. Chloride equilibrium potential is minus 70 millivolts. Potassium equilibrium potential minus 90 millivolts. Calcium equilibrium potential plus 132 millivolts. These are the equilibrium potentials of different types of ions. So again I am writing here the important point which I want you to know is, look, note, if membrane, if hypothetically I am talking, if membrane is permeable to only one type of ion, okay, then resting membrane potential of that cell, okay, the resting membrane of potential of that cell is equal to equilibrium potential of that ion. Okay, simple. In that cell, the resting membrane potential and the equilibrium potential, they are equal. They are equal. But in our cells, just now I have told you, not only one type of leaky channel is there. There is potassium channel, potassium leaky channel. There is sodium leaky channel and chloride leaky channel. So due to the presence of different types of leaky channels, you have to take them into consideration, and all of them will contribute to resting membrane potential. So one point which I want you to know is the leaky potassium channels are more in number, means it is more powerful. Actually it's more. So leaky potassium channels are more. So leaky potassium channels are greater than leaky chloride channels, and leaky chloride channels are greater than leaky sodium channels. So the numbers are more. Okay, potassium channel number is more, leaky potassium channel. So by this time you should understood. Okay, by this time you should understood. So if leaky potassium channels are more, means the cell resting membrane potential will be more towards the resting membrane potential of a cell is near to equilibrium potential of potassium, because potassium is dominating. Okay, for example, let me put it this way. See, potassium, it will create equilibrium potential of how much? What is the equilibrium potential of potassium? Potassium minus 90 millivolts. What is the equilibrium potential of sodium? Sodium is plus 63. Okay, let's put sodium here for better understanding. Let's write sodium here, plus 63. Let me write chloride here. What is the equilibrium potential of chloride? Minus 70. So minus 90 minus 70 plus 63. So what will be the resting membrane potential of this particular cell? You tell me. Now this particular cell, it is having 3 ions, 3 leaky channels: sodium leaky channel, potassium leaky channel, chloride leaky channel. So will the resting membrane potential be minus 90? Will the resting membrane potential will be minus 70? Or will the resting membrane potential is more near towards the plus 63? Where will be the resting membrane potential? Is it going to be towards sodium, or is it going to be towards the potassium? See, the resting membrane potential will be dependent on all these 3. They will finally balance and they will come to one value. But here in this cell, the number of the leaky potassium channels are more, hundreds and hundreds of times more than the sodium channels, than the chloride channels. So the resting membrane potential will be close to the equilibrium potential of potassium. Okay, will be equal to the equilibrium potential of potassium. Okay, for example, let me put it this way for better understanding. Look, imagine here is one cell. Okay, this one cell is having only one type of leaky channel, that's a chloride leaky channel. It's a chloride leaky channel. So now tell me, what is the equilibrium potential of this chloride? The equilibrium potential of this chloride is minus 70 millivolt. Okay, minus 70 millivolt. What is the resting membrane potential of this cell? See, as only one type of channel is present, this equilibrium potential will be the resting membrane potential. So in this cell, the resting membrane potential is also minus 70 millivolts. But again and again I am telling you, in our cell there are multiple types of leaky channels are present, but potassium leaky channels are more in number. So the resting membrane potential is more close towards the potassium. Okay, so that's the point. So resting membrane potential in our human cells, resting membrane potential in our cells is close to equilibrium potential of potassium. Okay, so with this we are done, but concept is done. Now how to calculate the resting membrane potential? You know how to calculate the equilibrium potential of a particular ion. So the concentration of ion outside the cell by the concentration of ion inside the cell, logarithm based on, you know, all this stuff like, you know, Nernst equation. But how to calculate the resting membrane potential? Nernst equation can be used to calculate the resting membrane potential? No. There is a different equation to calculate calculation of resting membrane potential, that is Goldman-Hodgkin-Katz. Okay, Goldman-Hodgkin-Katz equation. Okay, so this is just, you have to by heart it. So the voltage of the membrane, that's the resting membrane potential. Voltage of the membrane is equal to RT by F logarithm by permeability. Here we are also taking the consideration of the permeability of that particular ion, permeability of the potassium by the concentration of potassium outside the cell, plus I am not only considering the potassium because in the cells even sodium leaky channels are there. So permeability of sodium into the amount of sodium concentration outside the cell. Not only sodium leaky channels are present, but also chloride leaky channels are present. So permeability of chloride into the amount of chloride inside the cell. Okay, the amount of chloride inside the cell divided by divided by exactly opposite thing, the permeability of potassium into potassium concentration inside the cell plus permeability of sodium into the concentration of sodium inside the cell plus permeability of chloride into chloride concentration out of the cell. So this is 𝐒𝐵𝐻𝐼n𝐻𝐵𝐻𝐼n𝐻𝐾 equation. So this equation is going to help you in the calculation of resting membrane potential. Okay. So just know the name 𝐒𝐵𝐻𝐼n𝐻𝐾 equation is used to calculate the resting membrane potential of a cell. NERST equation is used to calculate the equilibrium potential of a particular ion. Okay, potassium equilibrium potential, you know the potassium equilibrium potential is -90, sodium is +63, chloride is -70 and calcium is +132 millivolts. Okay, to calculate this you require NERST equation. Okay, all these are the equilibrium potential or isoelectric potentials. Okay, so now after this let's discuss about resting membrane potentials of particular cells, important cells. Okay, resting membrane potential of some important cells. For example, let's say skeletal muscles, smooth muscles, cardiac muscle, that is a ventricular myocyte, cardiac muscle. The skeletal muscles, they are having a resting membrane potential all due to potassium, sodium as well as chloride. Okay, so resting membrane potential is -95 millivolts. Smooth muscle -60 millivolts. Cardiac -90 millivolts. Okay, next neuron -70 millivolts. Hair cells of the cochlea. Okay, hair cells which are present in the cochlea, hair cells are the receptors for sound. Hair cells, it is -15 to -40 millivolts, -15 to -40 millivolts. Next, your RBC -8 to -12 millivolts, and your photoreceptor cells, rods and cones, photoreceptors. Okay, rods, that is -40 millivolts during dark state, okay, during night, and -70 millivolts during light state. Okay, so these are the resting membrane potentials of different cells, and again I am telling you resting membrane potential is dependent on all the ions, all the leaky channels. Okay, not one thing. But here what I want you to know is, look here carefully, the resting membrane potential of a cardiac muscle. Okay, the resting membrane potential of a cardiac muscle, how much is it? It is -90 millivolt. So it is equal to equilibrium potential of, it is equal to equilibrium potential of what? Potassium. So potassium equilibrium potential is -90, cardiac muscle equilibrium potential is also -90. Okay, next look at the neuron. The neuron equilibrium potential is -70 millivolts, It is equal to equilibrium potential of, okay, it is equal to equilibrium potential of what? Chloride. Okay, so these are some important points which I want you to know for your exam. Equilibrium potential and resting membrane potential, they are not same. Okay, but in which cell equilibrium potential and resting membrane potential are similar? In neurons, the equilibrium potential, in neurons the resting membrane potential is -70, that is equal to the equilibrium potential of chloride, and in cardiac myocytes the resting membrane potential is -90, and that value is equal to the equilibrium potential of potassium. Okay, so with this we have discussed all the important points whatever you require for understanding resting membrane potential. And again I am telling you, in resting membrane potential, okay, in resting membrane potential, the point which I want you to know for your exam is Doran's effect. Okay, the Doran's effect is due to the presence of impermeable molecules like proteins, the distribution of permeable ions will become uneven. And finally, what happened to the chamber A and chamber B? Even though they are unequally distributed, they becomes electroneutral. Okay, electrically they becomes neutral. So there is no electrical gradient, but there is concentration gradient. Inside the cell there are more number of ions, outside the cell there is less number of ions. So because of this concentration gradient, I have explained, because of the concentration gradient, ions will move out of the cell. For example, in our human cells, potassium is more inside the cell, potassium is less outside the cell. So potassium is going out via the potassium leaky channels. The movement of this potassium out is going to create negativity inside the cell membrane and positivity out of the cell membrane. If you measure it, that will be the equilibrium potential. And the equilibrium potential of multiple ions will give rise to the resting membrane potential. Okay, so with this the topic is completed. Hope the video is helpful. In the next video, we will be discussing about resting membrane potential of neurons. Thank you.